Hello everyone, in this video tutorial we are going to present our proposed lossless intelligent comparison algorithm that we presented in IEEE 18th World Symposium on Applied Machine Intelligence and Informatics with the title of an artificial intelligence-based method for comparison of short strings. As is shown, this presentation is composed of 4 sections. In the first section, we explain about our motivation and the importance of comparison of short strings. In the next section, we propose our method in 2 parts. The first part is about the basic concepts of the algorithm, and the second part is about its intelligent performance. In the third section, we present the achieved results after applying our proposed method on short strings in different languages. And finally, in section 4, we present the conclusion. Okay, so we start with the definition of a string. If we imagine the string to be a string in ASCII mode that we can send a text in English, each character is composed of 8 bits, which can be either 0 or 1. The same rules also apply to Unicode, but the difference between the two is that the ASCII supports up to 255 characters, but Unicode supports 2 to the power of 16 different characters. However, in this presentation, beside ASCII, we discuss about 2-byte Unicode strings. But why the comparison of short strings is important? Well, the answer is that they are widely being used. For example, they are used in web pages, in social networks that have huge number of users, in smartphones, and also in expensive space communications, as these strings can support text in any language, and as they are widely being sent over the internet and occupy the bandwidth significantly. The comparison of these types of data is of great importance as it leads to reduction in cost, bandwidth utilization, and transmission time. For example, if we consider this scenario, which is an instant messaging network where there are several users that are sending short messages to a server. Here, as we have no information about the contents of the messages, and as the messages must be sent instantly, they cannot be compressed. The situation even gets worse when the number of users increases. Then we have to increase the number of servers as well. And as the servers must be synchronous, they start to communicate messages to each other, which applies more overload to the network and increases the bandwidth utilization. And now, as we have understood the challenges and as we are actually ready to start proposing our method and explaining the details of our method, we define the term tiny strings. In our paper and in the following of this presentation, tiny strings are those strings with the size of less than 160 bytes. So, to explain our method, let's consider the shown tiny string. For comparison of this string, our method creates an empty table which consists of 2 columns that are shown by 0 and 1. The algorithm starts reading the string from left to right and inserts the new characters into the table. Then for each new character, the algorithm considers its ASCII code, and when the character is repetitive, the index will be considered. So we have this string which consists of types 0 and 1. The type 1 represents the new characters and type 0 represents the repetitive ones. Obviously, at the time of transmission, the types must be none. Therefore, the first bit shows the type of character in this example. It is 0 because new characters are being read. Then the binary types of numbers are written with the length of the largest amount, which is equal to 7 in this example. Furthermore, when the type of characters change, the algorithm sets a flag with the length of the largest amount, 7 in this example, and then the header is set. In the next step, the binary number of indexes written and the length of the largest amount is set, which is equal to 0. And then the mentioned process continues till the last character. But there is a problem here. As we see sometimes, the length of the ASCII code is smaller than the length of the index and the header. As an advantage, our proposed algorithm considers this phenomenon and uses the smaller one while it compresses the string. However, there are still some challenges that must be faced. For example, when there is a large number like 20 in this example, all the binary lengths must be equal to the length of 20, while there are many small indexes in one region. In the following, we explain how we can find the regions with the small numbers and use shorter lengths for them. In addition, if we also consider the utilization frequency of characters in a table for a long time and set the most repetitive ones at the top of the table, then small indexes will be assigned to them, which increases the comparison rate directly. Also, it must be considered that whenever the algorithm starts to reorder the table, it must investigate to see if it's a good time or if it's efficient to reorder the table or not. These questions are important, as if the algorithm reordered the table when it's late, then there might have been a better situation before that time, which could have improved the comparison rate better than now. And if the algorithm do the reordering process when it's not efficient, then it's only and could be considered as an overload, because the table must be communicated between the servers and it increases the bandwidth utilization. In order to solve this problem, we aim to use artificial intelligence based methods, or specifically the neural networks, to solve this problem. To decompress the received string in the receiver side, the algorithm looks at the header. Here it starts with 0, so it probably means that the string starts with new characters. I said probably because, as I explained in the last slide, the length of the ASCII codes can be less than the index and its header. In that situation, the header is also equal to 0. In the next step, the algorithm checks the length of the strings and then sets them into the table, and finally, the decompressed string can be decompressed without any loss of data. We have provided this example to show you how the algorithm finds the regions with short indexes. This is a Unicode example, and we imagine that this Persian text is going to be compressed. Firstly, I should mention that in Persian language, the 3rd, 6th, and the 11th characters are the same. The algorithm inserts the characters into the table and considers their binary numbers in addition to the binary number of the indexes. So we have 4 types of strings. In this example, Cn shows the new characters, Cindex shows the indexes, Cindex NLB is the binary length of indexes, and CLB is the binary length of the characters. Then we have these 4 sets, and now, in this example, we would like to find out if it is efficient to send the SPU2 region, I mean the region with repetitive characters, by using indexes or not. So firstly, for a better understanding, we put the sets in this order and separated the repetitive parts of the characters that we want to check if it is efficient to send them by using indexes or not. By using these 2 formulas, we evaluate the separation efficiency such that F1 evaluates the size of the strings when the two regions are combined and F2 calculates the size of the strings when they are separated, then we can find out if separation of these two regions is efficient or not. In F1 formula, CNLB max is the maximum number in LB set, that's equal to 11. C index count is the number of indexes of the repetitive characters, which is equal to 3. C new count is the number of new characters, which is equal to 8. And C support is a variable that depends on the language. Here in this example, as we are using a Unicode string, it's equal to 5. But if you remember in this example, as we were using ASCII, C support was equal to 4. Moreover, in F2 formula, C new count is the number of new characters, which is equal to 8. C index LB max is the maximum number in C index LB set, that's equal to 4. And it has been multiplied by 2 because there are two regions here. And finally, if F1 was larger than F2, then it's better to separate the regions. On the other hand, the combination of regions is recommended. And now in this slide, we show you how the algorithm can find the maximum binary length in both sets of repetitive or new characters to check out if it's efficient to send them separately or with other characters. As is presented, we have 4 sets. CCN is the set of new characters, and CLB is the binary length of the new characters. C index n is the set of indexes, and C index NLB is the binary length of the indexes. Actually, the algorithm can check the efficiency of separation of the new or repetitive characters, but in this slide we consider and we discuss about the indexes or the repetitive characters. Now we consider these two sets. The first one is the index numbers and the second one is the binary length of the indexes. The algorithm considers a variable called max with the primary amount of negative infinity and starts to scan the set from left to right, and whenever it finds a number bigger than the amount of max variable, it updates the max. And in this example, it finds 2 points that maximum numbers exist, and it evaluates to see which one is the most efficient one for separation. In part 0, we would like to know if it's efficient to separate index number 12 or not. And the algorithm finds it by using this formula. This formula shows that how many bits can be reduced by separating the index with maximum binary length. In this formula, CULB max 2 is equal to the amount of the second update of max, which is equal to 4 in this example. And K is the number of repetition of maximum number, which is equal to 1. And count is the number of indexes in part 0, which is equal to 4. Moving forward, CULB max 1 is the first update of max, which is equal to 2. And C support is equal to 5 as Unicode strings are considered in this example. As is shown, the formula becomes equal to 0, and it means that there is no difference if we separate index number 12 or send it with other indexes. But as we see, in the second calculation for separation of index number 17, 13 bits can be reduced, so the algorithm separates the index number 17. So as a general view, we see that there is a string which is a poet in Persian language. Then the algorithm converts it to the Unicode, sets it into the table, and by doing the calculations, the suitable point for the separation could be found, and finally the binary amounts will be sent. And now we discuss about the intelligent performance of our method that plays its role in the reordering process of the table. It actually aims to find out when it is a good time for the table to be reordered. If we consider this example, the algorithm puts the number of repetition of characters into a column, and then we have this set. In the next step, the algorithm sorts them in descending order and informs the receiver about the changes. In order to find out the best time for reordering the table, the efficiency of the table order on that time must be investigated. For this purpose, the shown sorting quality formula calculates the quality of the table order. We show the performance of this formula with 3 examples. In these examples, index use is the frequency of the repetition of characters, and n is the number of characters. In the first example, the most repetitive character is in the last, and the least repetitive one is in the first row of the table. As we see, in the second example, the table has the best order, and in the first one, it has the worst. In this example, the sorting quality formula is calculated in this way. The denominator is always equal to 45 because n is equal to 10 in this example. And denominator is calculated in this way. For instance, in the first example, as 1 is less than the other 9 indexes, so here we have 9. Then 2 is less than the other 8 indexes, so we sum up 8 with 9, and so on. This rule also applies to the other examples, and the sorting quality formula can be calculated in this way. In order to change the order of the table after sending beta number of characters, the sorting quality is calculated, and if sorting quality was larger than alpha, which is a number between 0 and 1, then the table gets reordered and the receiver will be informed. It must be mentioned that the alpha and beta values can be achieved by trial and error. Till this part of the presentation, we have uploaded the source codes on GitHub, and the link is available in the caption of this video. Now we explain how artificial intelligence methods can be involved in this process. We imagine that there are several tiny strings that are going to be compressed. In the first step, the sorting quality is efficient, which is shown by white. After sending beta recognition characters, the sorting quality gets worse, but is still acceptable and better than alpha. Finally, the sorting quality becomes bigger than alpha, which means that the table is in the worst situation and the table must be reordered. The algorithm repeats this process continuously till the end of the strings. In the next step, our proposed method starts to extract information to train the neural networks in order to find out when it's a good time for the table to be reordered. In each part, after sending beta recognition characters, the algorithm calculates the sorting quality and the comparison rate, and also considers the number of sent characters, and as the quality of table order is acceptable, the table sending variable is false. This process is repeatedly done till the sorting quality value is in the worst situation. Here, the sending of table is true, which means that the table must be reordered and sent to the receiver. This is the information of period 1, in which sorting quality and comparison rate are calculated for one time. And as we see here in the last part, when the situation gets worse, the sending of table is true, which means the table must be reordered and sent to the receiver. The discuss process is done for all the periods, and finally in period K, after sending beta recognition characters, the algorithm sets the information as the inputs of the neural network. It sets the comparison rate and sorting quality as the inputs of the neural network, and the neural network predicts the number of sent characters. If the current sorting quality was better, then we update it in the neural network to improve its performance for future predictions. And we recommend using online training methods for this process in the future works. Indeed, we proposed utilization of the neural networks to find out when it's suitable to check this if condition in this process. Here you can see the experimental results. The first table shows the dataset, and in the second and third tables, we compared our proposed approach with LZW and Huffman methods for comparison of Unicode and ASCII strings. As you can see here, our method has improved the comparison rate, but in contrast, it increased the runtime. But it must be mentioned that for the transmission of real-time text, this runtime is insignificant in comparison to the transmission time, as the compressed strings can be communicated much faster. To conclude the presentation, we proposed a comparison method which is suitable for reducing the size of ASCII and Unicode tiny strings. This method does not need to do any statistical analysis before beginning the comparison process. It actually improved the comparison rate in comparison to other previous methods such as LZW and Huffman, and it's completely independent of language, and any text in any language can be compressed with this method. As an important advantage, our proposed method provides no overhead for lossless comparison of data, and by using artificial intelligence methods, it improves the comparison rate during the time.